In 5G networks, massive MIMO technology enables connectivity for a large number of users. However, as the number of beams increases, interference can become a major issue, degrading network performance. Imagine a scenario where multiple UEs are distributed across two neighboring cells. Each UE moves along the trajectory indicated by the orange arrow, demonstrating its mobility. However, when UEs are in motion, it becomes challenging to acquire precise channel state information. This leads to the formation of inaccurate beams. Additionally, due to the rapid mobility of UEs, the connection between the UE and the base station can quickly become outdated. In particular, when UEs converge on the same location, beams from different base stations overlap, resulting in interference. To address these challenges, we train an AI system. Using an AI RIC adapted to UE mobility, we first update the association between base stations and UEs. Then, based on the established association between base stations and UEs, the base stations determine the angles for beamforming. The AI RIC continuously performs beamforming using this two-step approach. If, during the association update process, the serving BS for a UE changes, a handover command is issued. Subsequently, beamforming commands are executed based on the updated association. In conclusion, this hierarchical beamforming structure mitigates interference by eliminating overlapping beams and saves power by deactivating redundant beams. On average, this leads to an improvement in overall network downlink throughput and a reduction in transmission power consumption. Using the Viavi RAN Scenario Generator, RSG, we simulate a realistic 5G RAN environment. In this scenario, 3 mobile UES are served by 2 base stations, with each user connecting to one of the 2 BSs. Through RSG, we generate mobility patterns for the 3 UEs, with the orange lines representing their movement paths. Each base station employs massive MIMO and operates on the FR1 band. Now, let's start the simulation. During the RAN simulation, UE reports provide RSRP and position information for each UE. These data are delivered to the AI RIC's feature extractor, which then extracts features related to mobility patterns. Upon receiving these input values, the association between base stations and UEs is first computed. Then, using both the extracted features and the association data, the beam angles for each BS are determined. The computed values are aggregated, and the association with base stations and UEs, along with the beamforming actions, is delivered to the RSG. Once these actions are applied in the RAN simulation, network performance is evaluated through cell reports. The downlink throughput and average transmit power values from the cell reports are fed back into the system to train and fine-tune the model's parameters. The beam optimization process is updated every step, while the feature extraction and association between base stations and UEs are updated every several steps. This approach enables stable and cost-effective learning. Next, we compare network performance with and without AI. The top section represents the scenario without AI, while the bottom section shows the AI-enhanced network. On the left, we visualize UE movement and how base stations serve them. On the right, we track the average transmit power over time. Using Viavi's AVE console, we can clearly see the impact of AI-based interference mitigation. Downlink throughput improves by an average of 23%, while unnecessary beams are reduced, leading to a 43% decrease in transmit power. As the number of connected users continues to grow, massive MIMO remains crucial, but so does effective interference mitigation. AI-driven interference management not only enhances energy efficiency, but also boosts network performance. By integrating AI into RAN optimization, we take a step toward the next generation of intelligent, adaptive, and highly efficient wireless networks, ensuring seamless connectivity in the 5G era and beyond.